All right, here we go, lesson 231, motor branch circuits. This time we're going to talk about overcurrent protective devices, short circuit, and grounding fault protection. So really, when it gets down to it, we're going to talk about breakers and fuses here. How do we size those for motor circuits? So right off the bat, we have some tables we need to reference. Table 430.248, that should look familiar. That's your full load current single phase. 430.250, full load current three phase. Now we're going to introduce 430.52. That's actually going to give us the maximum breaker or fuse size for motor circuits, and we'll take a look at that here in a moment. And then last but not least, table 240.6a is going to give us standard overcurrent protection ratings, because we're going to have some odd numbers for our calculations that don't always add up to a nice even number, that they may not make a breaker or fuse in that size. So we need to check that to see what is the next higher standard size. So, just as a review, here's our table 430.248. We're going to find our full load current based on voltage and horsepower. Same thing in the three-phase table. Again, that should be a review from last lesson. Now it should be a new one for us. I think you guys hopefully remember this from year one. This is our maximum rating or setting of motor branch circuit, short circuit, and ground fault protective devices. In other words, your fuses and your breakers, depending on what type you have. We're going to sort of check out how to use that table. How do we get there? I think the best way is really look at some examples quickly before we do that. Here's your standard overcurrent protection device sizes. So if we come up with, say, 32 amps as a calculation, what's the next higher size? Well, 30 misses it, so we got to jump to 35. So things like that we can check. So, a review, that's all the four tables we will need to reference here for our next example. So here's an example with some motor nameplate info. Let's say it's 115/230 volt, single phase, 3 horsepower. It's supplied by a 1-pole breaker and a 120/240 panel. Maximum size, inverse time, circuit breaker permitted is blank amps. So it's up to us to determine how many amps do we need. ITCB, inverse time circuit breaker. So let's first pick out some important info. We obviously don't need all this info, but important. I'm going to point out this is a single phase motor, 3 horsepower we're going to need to know. It's supplied by a 1-pole breaker and a 120/240 panel, which tells us it's a 120 circuit. And then lastly, we need to know that it's going to be an inverse time circuit breaker. So what's our first step here? Since it is single phase, let's find out what our full load current is going to be. So we reference 430/248. We know that since it's hooked up to a 120 circuit, the motor is going to be rated 115, so we're going to check our 115 volt column. We know that it's a 3 horsepower motor, so we check the 3 horsepower row, and we can see that this full load current for this particular motor would be 34 amps. So we'll plug that in here to our page. So next thing we need to see is we need to check 430.52. That's basically going to give us a multiplier or a percentage of how much bigger our breaker needs to be than the full load current. So once again, we know we have an inverse time breaker, so we're going to come to this column. We have a single phase motor. Notice until you get down here to these wound rotor and DC motors, the percentages are pretty much constant across the board, especially for single phase and AC polyphase, which is 3-phase. So for our purposes, the row is not too big of a deal. But regardless, we get 250%. So we need to come back here and multiply our 34 amps by 250%. Pretty simple. That comes out to be 85 amps. So off the top of your head, is that a standard overcurrent device size or not? Well, if you don't know, we have the tool to check that. That would be table 240.6. And we can sort of go through, and we need one that is going to be at least 85 amps. We come short by the 80, so we got to jump to the 90 amp breaker. That's our selection. So we're going to use a 90 amp breaker, inverse time circuit breaker for this particular motor. And that's about as simple as it is there, guys. So I think that's a pretty straightforward approach. You really just need to make sure you have those 4 tables bookmarked or noted. And beyond that, just check the tables and do your math carefully.